Okay, let's get started here. So project number 3 is due on Friday, November 22nd at noon. Let's just take a quick look ahead of where we're going in the semester. Test number 3 will be December 4th. It will be over the cluster analysis section, the discriminant analysis section, which hopefully we will finish today, the nearest neighbor analysis section, and the logistic regression section. So you can see, in terms of, we'll have 4 main topics. After today, we will be done with 2 of the main topics for test number 3. So that's coming up rather quickly. Are there any questions before we get going here? Okay. So we left off last time on approximately page 24. So far what we've talked about is the most basic discriminant analysis methods. We would like to now be able to generalize this to allow for some flexibility in how we approach our problem here. And we're still going to keep with 2 populations. I'll talk about a little bit more than 2 populations later today, because that obviously is part of the project. And to set the stage for them for the first generalization that we're going to talk about, let's talk about in the context of, let's say, being diagnosed for an infectious disease. And let's just talk about HIV testing. And let's say that a new HIV test is being developed. And if it's being developed, that means it needs to go through some clinical trials. So test it out, see how well it does. And let's say there is some other HIV test out there, and there are, which will give you a definite result of, let's say, that you have HIV or not. And so what we like to do is look at how does this new HIV test perform in comparison to what's often referred to a gold standard. And so with this then, if we, let's say, give the test maybe to 100 people, we could summarize the results in a table such as this. Let me get my red pen out. So on the rows here we have, well, what's the actual outcome for a person? Either they have HIV or they don't. And then this new test comes along, and either you're going to get an HIV negative or HIV positive result back. What you're hoping for is that people in the clinical trial will only fall into the orange squares there. So for example, if the test says HIV positive, you're hoping that truly, in fact, they do have HIV. If the test says HIV negative, you're hoping that truly, in fact, they are indeed, they do not have HIV. But the problem is that diagnostic tests for infectious diseases are not 100% accurate. And so you will have people that fall into these green squares there where there's an error. So for example, let's say a person does not really have HIV, but their tests came back positive. This is what you often will hear referred to as a false positive. You could also have a false negative, where a person does have HIV, but the test actually comes back negative. So we want to minimize these kinds of errors. In some situations, in particular, especially for infectious disease testing, some of these errors, or one of these errors, is more important to prevent than another. In particular, well, both errors you don't want to have happen. In particular, the most important error that you want to control for is that particular one, where a person does truly have HIV, but the test says negative. The reason being is because now the person thinks that they don't have HIV because the test came back negative, and so therefore they're not undergoing particular treatments that would help them out. Also, obviously, then too, it leads to, let's say, this particular person could be infecting others then unknowingly. So we wanted that kind of error is more important to control than the previous kind of error. But again, both errors are definitely important. So what can we do then? Well, what we can do is, as you'll see shortly, is assign a cost. A cost for a misclassification. So for example, the cost for the false negative outcome, let's say we'll just assign a number 5. The cost for a false positive outcome might be assigned a number of 1, meaning that the false negative is 5 times more important to control, you could say, than the false positive. So what we're going to talk about today is one way that we can include cost into the discriminant analysis method. Another thing that we would like to be able to do, so this is a second generalization, is to take into account that the populations that we are sampling from might not necessarily be, let's say, equal in terms of population 1 versus population number 2. There might not be, let's say, the same amount of people. So for example, especially with HIV, obviously you know that the proportion of people in our population here in the United States, let's say, that have HIV is rather small, less than 1%. So it would be nice if maybe you could somehow take that into account into your analysis. And so we'll look at how we can do that shortly. We'll look at a third extension a little bit later to our discriminant analysis methods. Okay. So when I was going through my lecture notes last night, I decided that I wasn't necessarily as happy with how I organized stuff as I was when I first wrote up the lecture notes. So you're going to see some changes. They're minor. Often it's just a matter of rearranging stuff. Okay? So what you can do is the stuff that's on bottom page 25 you can cross out, but the stuff that's highlighted in yellow is actually going to be moved down to where you see Bayes' rule on page 27. So the stuff that's highlighted in yellow is going to be moved down to where you see Bayes' rule on page 27. Sorry, these things happen when you put together a set of lecture notes. I just decided I didn't like the organization that I had, and I thought there was some stuff that I didn't need to really talk about either. Okay. So, how do we include then the cost of a misclassification? In other words, a numerical penalty for making a particular kind of misclassification. Well, let's define C sub I given J as being the cost of classifying an observation in population I when indeed the observation should have been population J. In other words, if I were to define this, C sub 2 given 1, what that means is this is the cost of misclassifying observation population 2 when in fact it should have been population 1. This is going to be a numerical value. We're obviously just using symbols for now so we can make this a general presentation. But this is going to be a numerical value. Of course, you could also have then the costs of a misclassification for an observation that came from population number 2. Right? Accidentally, let's say, misclassified it as population 1. Now note that if I were to look at, let's say, C sub 1 given 1, that's going to be 0 because, hey, I got it right. Why would I want to assign a cost to it? I want to get it right. Okay? Same thing for C of 2 given 2. Note that the stuff that I did cross out, I should have mentioned, I should have highlighted in yellow, it's actually going down there. Okay, so I'm going to define a numerical cost. And as you'll see shortly, I'm going to be including it in my methods to do this discriminant analysis shortly. Also, I like to be able to include, again, the fact that oftentimes, there's not, let's say, an equal proportion of, let's say, observations from one population versus the next. So like with the HIV example, if I were to just, let's say, simply take a random sample of, we'll say, 10,000 people from the entire United States population, only maybe about 1% of them will come back as HIV, that they have HIV. And so I like to define, let's say, a prior probability, because this stuff is often known, define a prior probability that takes this into account. So with the HIV example, I might say, if let's say population 1 was HIV actual, and yes, they do have it, P sub 1 could be, let's say, 1%. P sub 2, for the people who don't truly have HIV, could be 0.99. Now, another place where this can occur is as follows. Let's say you have specifically, let's say you have a sample size of 100, where you specifically try to take a sample of 25 people randomly from population 1, 75 people randomly from population number 2. What that means is that since you're controlling then how many people you're getting in your sample from one population or the next, you should take that into account in your sample, because in actuality, you might not necessarily have, if you took a random sample for everything, you might not have 25% from one population, 75% from another. So this is another case or another situation where you would define what P1 is and you would define what P2 is, corresponding to how you took the sample. Is that clear? Any questions about that? Essentially, it's like a stratified random sample in those cases. Okay, so P sub I is going to be the prior probability that a randomly selected observation belongs to population I. Okay. Now, with this setup, then, we can define an average cost of misclassification. So on average, what is the cost of having a misclassification overall? And so to do this, let's define P sub I given J as a conditional probability. You've seen conditional probabilities in the class such as Set 801 before. It's going to be the probability of classifying an experimental unit in population I when it should have been in population J. So again, just to make sure this is clear, if I have P sub 1 given 2, the best notation in the world, but I think it's okay for what we need to do. P sub, the probability of 1 given 2 is the probability you classify an observation population 1 given it should have been in population 2. Okay? Now with that then, here is then the average cost of misclassification. Take your prior, population 1, notice the subscript here, take it times the cost of misclassifying an observation into population 2 when it should have been population 1, times in the probability that you actually do that, the probability of a misclassification to 2 given population 1. And then we add then essentially the same thing, but now notice this subscript. Notice where the 2's and the 1's are. We're just kind of reversing them. Okay. So that's the average cost of misclassifying observations. Where does this come from? Why are we using this equation? Well, I'm going to first talk to those students who are stat majors and who have taken stat 883. Then I will talk about, in general, an intuitive way to think about it for those of you who have not taken stat 883. For those who have taken 883, this is Bayes' risk. Just maybe presented in a little bit different form than what you've seen maybe in the past. But if you look at Casella and Berger's book, I assume that all of you talk about Bayes' risk. Does this sound familiar amongst the stat students? You didn't get to it? Oh, no. This is a topic that is typically taught in every Stat 883 course, but I guess obviously not ours. Well, for those of you who do have a copy of Casella and Berger, take a look at Bayes' risk after class. You're going to see some similarities. Let's see, how should I explain this now? Oh, let's see. Okay, just give me a second. Again, I'm talking more towards the students who should have had this in 883. But obviously, if you haven't had 883, you can still obviously listen here. Some aspects will make sense, and then I'll draw an intuitive explanation of it. I assume that all of you have taken 883. You've talked about Bayesian analysis, at least a little bit. Okay. Like a Bayes estimator. Does that sound familiar? Okay, good. You've talked about loss functions. Loss functions? Loss functions? Maybe. Well, a loss function then is simply it's actually, in our case, it's going to be the cost function here. It's a way to penalize yourself for getting something wrong. So, for example, squared error. Let's say that you're trying to estimate a parameter theta with theta hat. A squared loss function that measures how far theta hat is from theta is, as you expect, theta hat minus theta squared. Okay, that's a loss. That's one commonly used loss function that all of you have used before, even if you didn't know it was called a loss function. There are other loss functions, such as I can make that an absolute value instead. And so, what you might be interested in is, well, what would be then the what would be the average loss from using a particular estimator called theta hat? What would be the average loss? And this is what's called the risk function. Anybody heard of a risk function before? Okay. So this is a risk function. And then what Bayes risk then is the expected value then of the risk function. Okay, taking into account the prior distribution of your parameter of interest. Okay, and so it seems to be to choose an estimator, a Bayes estimator. A thing that would be of interest to do then would be to find the estimator that minimizes your expected risk. And then that, again, comes to the idea of Bayes risk. Okay, enough about that. In the context of Bayes risk then, in terms of what we're doing, your prior distribution, typically you say, let's say theta is distributed tau of theta in a Bayes situation, your prior distribution in our case is simply P sub I. The prior probability of being from population 1 or from population number 2. The loss function, again, is your penalty for getting something incorrect, essentially, is our cost function here, where we simply would, let's say, give it a numerical value in our more simple setting. And then a probability density in a Bayes situation, let's say you have f of x given theta, your probability density is this conditional probability, the probability j given I. So if you put this all together then, what you have is this. So what I define as the Bayes risk above, now I'm just putting it in a summation form. Now how many terms are going to be in that summation? I'm taking the sum from I equal 1 to 2 and j equal 1 to 2. So how many terms? 4. But 2, yeah, thank you for pointing out. 2 of them are 0 because the cost function will be 0 when you get a correct classification. So that's why you only see 2 actually listed here. Okay? But it's the same exact expression. I'm just putting it in a different form so you can equate it to a Bayes risk situation, what you would have hopefully seen in 883. And so what I can do now, since P sub I is only dependent upon I can move that out of the inner summation. And then what we have in the inner summation left is what's called the risk function. Essentially, it's your average loss, your expected loss function. And then so, then what we're left with then is the average risk then, where I'm using the p sub I basically in the role of tau of theta. Okay. So I kind of also gave them the intuitive expression or intuitive explanation too that I was planning to give for those students who hadn't taken Stat 883, but just to review. Essentially what we want to do is we have costs assigned to making mistakes. We have the corresponding probabilities of making those mistakes. So it seems intuitive then to say that the average cost that one would have is then just simply take into account then the probability that it happens, and also then take into account the prior probability that you will have an observation from one population or the next. So that's my explanation of where this is coming from. And hopefully it makes some intuitive sense to you then that we want to minimize, we want to come up with a discriminant analysis rule, let's say, or a method that minimizes this average cost of misclassification. The rule that minimizes it is, you could say, the best rule. And this rule is called a Bayes rule. Okay, so remember that first stuff that I had put into in yellow, highlighted in yellow. This is where it goes, and it's just a notation thing. Let's define two probability densities. We'll say F1 is for population 1, F2 is for population 2. You'll notice I have a theta 1 and theta 2 in there. This is just a general way that I'm using to say this density is dependent upon some parameters. Okay? You could say that F1 is multivariate normal, where the theta 1 that I have in there could be could represent, let's say, the mu1 and sigma 1. You could say F2 is multivariate normal as well, with mu2 and sigma 2. But to actually write this out, at least first of all, you don't even have to say exactly what the density is. Eventually we will say, okay, let's just make it multivariate normal. But in general, you don't have to. Okay, so this is the rule. I'm not going to get into why. I'll give you some intuitive explanation for why this is a rule. But again, for those of you who've had like an 883 course, this is in Cassell and Berger, how to come up with a Bayes rule, how to minimize that average cost of misclassification in our case. This is directly from there. So, simply, my discriminant analysis rule says, choose population 1 if P2 times the density for population 2 times then the cost of misclassification, if it actually came from population 2, if that is less than P1 density for population 1 times then the cost of misclassification if it came from density 1. Choose pi 1 if this occurs. If it doesn't, choose population number 2. Okay. Now here's the intuitive explanation for what's going on. Hopefully you remember the likelihood rule that we started off with on page, I'll just give you a quick reference, on page 4. And basically what we had on page 4, we had two densities. They were multivariate normal. And we said choose a particular population for an observation of interest for corresponding to where you have a larger value for the density. We equated this to using a likelihood function or maximum likelihood estimation. So what I have just presented to you is exactly the same as what we had on page 4, except for now I have a P2, I have a P1, I have a cost. So if we let's say the cost be equal, if we let P1 and P2 be equal, then what I just presented to you is equivalent to what we had on page 4. So as you might imagine that if P1 and P2 are not equal, if the costs are not equal, you would imagine that there are some modifications that you would make. Well, there's the modifications. So that's That's the intuitive explanation. A more mathematical explanation would be given in a book like by Cassell and Berger that would be used for set 883 here and across the country. Okay. So we have a new discriminant rule that we can use. Let's also add an assumption of multivariate normal populations, and sigma 1 is equal to sigma 2. And now our rule becomes this, something that looks like Mahalanobis distance rule, where we take our Mahalanobis distance, and then there are some simplifications that occur. You can go through the math. Some simplifications that will occur. So you get the Mahalanobis distance now minus the log of p sub I times c of j given I. That's my distance. And again, the smallest distance then corresponds to the population you classify that observation into. Just like what we did before with just straight up forward Mahalanobis distance. Sure.
Looking on page 5, the Mahalanobis distance is kind of 1/2 in front of it. Where's the 1/2?
I will. It doesn't. I believe what happens is this: when you go through the math, if you notice, if you only have Mahalanobis distance on page 5, does it really matter if you have 1/2 there or not? Now it does matter because we have this extra stuff there to worry about. And if you remember, for example, in a multivariate normal, you have e raised to the negative 1/2. So that doesn't fall out. Okay. So it's just a minor, in a mathematical sense here, it's just a minor little thing that you're additionally including here in your distance measure to allow you to be more general. Now, how can we implement this in R then? Well, when we first looked at the LDA function, I said to you there was an argument called prior. I said, well, don't worry about it right now. We'll eventually get to it. Oh, this is when we're getting to it. And with the place-kicking data set, I simply set prior equal to basically a vector of 0.5 and 0.5. That corresponded to P1 and P2 that we see now. Okay? Just a second, I don't want to get ahead of myself here. So, you have a way that you can set what the prior distribution is. I'll talk a little bit more about how you choose that coming up. But you have a way that you can set it. Now, one thing that you have to be careful about, because it's not maybe necessarily clear, is, well, what does R think of as population number 1? And what does R think of as population number 2? How does it make the choice? Okay? Well, with the place-kicking data set, if you remember, our good variable had 2 values, 0 and 1. So it makes sense. What R does, it basically looks at your good variable and it puts them into numerical order. You have a 0, you have a 1. So 0 is going to be population 1, 1 is going to be population number 2. So the first thing that you put in here for the prior here corresponds to the failed place kicks. The second thing that you put in there for the prior corresponds to the successful place kicks. Is that clear? Okay. But now this gets into, it becomes more complicated here. And it requires some understanding of how R treats character variables. I use it as a general term. R will call these factor variables. If you've had me for set 870 and 875, you've heard me do this discussion before. I'm going to kind of just do it again here because I know there's many of you who have not had me for a class in the past. And simply, what R does is sees, well, what is the variable that you're using in LDA as, determining what the populations are. It looks at that variable, it transforms it to a factor, which means even if it's a numerically measured variable like 0 and 1, it essentially, let's say, puts quotes, you could say around 0, puts quotes around 1 to transform it to a character, or in R's terminology, a factor. And then R orders everything orders the different levels of your factor. And this is how it does the ordering. It puts the numbers first. So if you had, let's say, for some reason you had, let's say, the number 10 and 99 for some odd reason as a way to symbolically denote your two populations, it will treat population 10 as will treat 10 as population 1, will treat 99 as population number 2. Okay? But what happens if you had some character, actual letters in there? Well, that's how it does the ordering here. So for example, if you had as the variable in your data set that denotes the two different populations, let's say that you had let's see, how do I want to do this? No, we'll just do this. Let's say you had two levels, a lowercase b and an uppercase b. I don't know why someone would do this, but let's say it was that. It would treat population 1 as the lowercase b, population 2 as uppercase b. Okay? No, 10 would be less. Now, a good way to help show you how this all works is I have a program on my website called factors.r. And let's just quickly go through some examples. Let's say that I create a data frame and I've just thrown in there some some values for a variable that I call cat.var for categorical variable. So you can see D, A, and so on. You also see some lowercase letters as well. It's just a simple data frame. Has 10 observations in it. And then I ask R, tell me what the class of this particular variable is. Well, R sees that you have quotes around stuff. So it saws that there's letters in there, so it says, okay, this is a factor. Well, what are the unique levels then of the factor? That's where the function levels can be used. And notice how it does the ordering there. So in a case that, let's say that you had 7 different populations for some reason in a discriminant analysis, and you use these as the codings to denote which populations, R will treat them population 1 as 0, population 2 as 1, population 3 as capital A, and so on. Let's look at another example. Let's say that, and this is like with the place kicking example, let's say that we have just 0s and 1s to denote the different populations. And so I put them into another data frame called num.var for numerical variable. Notice when I use the class function with it, it says, okay, it's numeric. Because R doesn't know that indeed that these are basically a simple way that you are denoting which population is for which observation. And so if I then apply levels to it, we get null back. Meaning, okay, wait a sec. R says, wait a second here. You're asking me to tell you what the levels of this categorical variable is, but obviously it's numerical. So what R would do in our LDA function, and we'll do in other situations as well, it will actually on its own transform then this variable to be a factor. And the way that if you really wanted to do that on your own, the way that you could do that is to use the factor function. So now we have these levels of our particular variable, and we have levels 0 and 1. If you actually use then the levels function with all this, you see the quotes. Excuse me. So, a little bit of background on how R works. In any kind of software package, it's not always necessarily standard, how it's done across software packages, but obviously you can see it's important to know how a software package handles this kind of stuff. Not every software package is going to be the same. So anyway, that's why I wanted to take the time to talk about this. Okay. Now, while I went through this large discussion about basically how you set your prior probabilities, what I will tell you is that generally speaking, unless you have other reason to believe otherwise, generally speaking, you go with what's called priors proportional to what was observed. So, for example, if I have a sample size of 100, I observe 49 from populations 1, 51 from population number 2. Typically, what will be done in practice, because it makes sense, is that you're going to let R use priors that are proportional to what was observed. So the priors so P1 would be 0.49, P2 would be 0.51. This, in fact, is the default for LDA, to have priors proportional to what was observed. Again, it makes sense to do that if you're simply taking a simple random sample from your populations. If instead you took a random sample from population 0 separately, where you specifically wanted, let's say, 25 observations, and if you took a simple random sample from population 2 separately, where you wanted 75 observations, then you should take that into account then by setting your priors to be corresponding to that. Okay, so please be careful about that. Okay, so that's how you deal with prior probabilities. Just a second. Well, what about costs? How do you include costs into your discriminant analysis in R, or actually any other software package? Typically, most software packages are not set up so that you can easily say, my costs of misclassifying into population 1 when it should have been population 2 is some numerical value. Typically, software packages are not set up that way. And so what you have to do, and it's actually not too difficult, is that you can change your prior probabilities to reflect the costs. And this is simply how you do it. Essentially what you're doing is you're just rescaling your prior probabilities. Obviously, your prior probability should add up to 1. So how about we weight them by all the costs? And then we look at, well, what proportion then for population 1 would be then the corresponding cost of making a misclassification in population number 2, accounting for the prior. So you just take that ratio, and that's your, let's say, your new prior probability that you would use in the priors argument of LDA. Do a similar thing then for population number 2. I will not ask you a question about this on the test. This will be the last time that we see this part right there. The reason being because, as you might expect, it's difficult to figure out what should I use for costs. How much more is the cost for this misclassification versus this misclassification? That's a difficult thing to determine. And you can see, there's leeway that one person might say one thing, another person might say another. And so because of that, I don't think it's necessarily worth our time to explore this any further. But I did at least want to mention to you, it is possible you can do something like this. Okay? So what you're responsible for is to know that indeed you can set costs, but we're not going to bother with actually looking at examples involving them. Okay. So we've looked at 2 generalizations, prior probabilities, costs. Here's the third one. Well, what happens if your covariance matrices are unequal? So we still have multivariate normals, but what if your covariance matrices now are unequal? Well, you essentially can use the base risk just like how we had set up before, and then again through using the through using the Bayes rule, I should say, on page 27, how we had set up before, but now you just have two different covariance matrices. And what ends up happening is this. You're just using some math. Your new distance that you have, just like Mahalanobis distance, now has an additional component that we did not have with the last distance that we looked at. And it kind of makes sense. Notice now you have to take into account unequal covariance matrices. So, again, the way that you use this then is that you find the two different distances. The distance that's smallest corresponds to the population you classify the observation into. Using this version of a distance to do the discriminant analysis is what's called quadratic discriminant analysis. So if you remember before, I actually used the term linear discriminant analysis before. The reason being is because when I would write out b prime x minus k for the linear discriminant rule, you can see that I'm taking a linear combination of your variables, x's. Now, if I were to do the same thing here, incorporating the unequal covariance matrices, you could write out a discriminant rule just like what we had seen previously. And what you will see is it's dependent upon quadratic terms of your x's now. I chose not to actually show this to you because I think it's just simple to apply this, to think of it in terms of distances instead. And so I just decided just to show you the distance itself. But I wanted to at least briefly mention where the name quadratic discriminant analysis comes from. Okay. So, with linear discriminant analysis, we had a function called LDA that did it. With quadratic discriminant analysis, we have a function called QDA that does it. So now you might be thinking, when is he going to get done talking? Or you might be thinking, well, how do I make the decision of, should I use equal covariance matrices or unequal covariance matrices? This is not necessarily an easy choice. Immediately you might think, well, why don't we just do a hypothesis test for it? Yeah, you could do that. In fact, if you ever end up using SAS and Proctor-Scrim, which does this, Proctor-Scrim on, I think, page 2 of the output will have a whole page devoted to this particular hypothesis test. Simply, here's what the hypotheses look like. So you might think if you reject HO, use quadratic discriminant analysis. If you don't reject HO, you might be thinking, no, it might be kind of safe to use linear discriminant analysis. But unfortunately, with this test, obviously it relies on I haven't said this yet. It actually relies, it's a likelihood ratio test. It relies on a multivariate normal distribution assumption. As we talked about, that's not necessarily always realistic. Fortunately, these discriminant analysis methods are fairly what's called robust towards non-normality, so they tend to work well still. But this is something different. This is now a hypothesis test, and this test can be sensitive to non-normality. So that's one problem. Another problem is that, and we've discussed this before a little bit, the difference between practical significance and statistical significance. So if you have a very, 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 very large sample size, you're eventually going to reject HO. That's the problem with hypothesis testing. When you have an equal versus not equal for hypothesis, you're going to be able to find some sample size in actual application that you will reject HO. And so then the question comes, well, even if I reject HO, is it really meaningful? So just to make sure you understand what I mean, let's talk about testing for means. So let's say that a true mean for something is 3.000001, and your testing is mu equal to 3 versus not equal to 3. And maybe we're thinking in terms of GPAs here. If you reject HO, is it really meaningful? No. Okay, you should all be shaking your head no. It's not very meaningful. Yeah, sure, the mean is different from 3.0, but how different is it? It's not very different at all. So in this case, it's not practically significant. It is maybe you'd be able to find a sample size where you do find statistical significance, but it's not practical. That's one of the problems with hypothesis testing. That's why, hopefully, this instructor who taught you 801 said this to you. You should, whenever possible, use confidence intervals, because a confidence interval will allow you to see this. What the true value is for mu, versus a hypothesis test simply until you reject or don't reject. So, because of this, you will typically, because of these problems, typically you will see people say, okay, it's not even worth your while to do this hypothesis test, even if the SAS gods tell you to do it. But it's typically not worth it to do it. Instead, what you should do, and this is actually recommended in Dallas Johnson's book, which is based upon using SAS, just simply do linear discriminant analysis, do quadratic discriminant analysis. Do them both. Your ultimate goal, remember, is to find one method that gives you the lowest misclassification error rate. Or equivalently, you could say your goal is to get the highest classification correctness. That's your goal. So I don't care if the covariance matrices are equal or not equal. I don't care which one it tells me. Just do both and pick the one that gives you the best classification rate. Okay. Is there any questions?
No. The quadratic is not necessarily better.
It will not necessarily be better, even if it has more terms. You can think of it this way. If truly you had equal covariance matrices, I would expect that linear discriminant analysis would work a little bit better. The reason being is because you're estimating less parameters. And I don't know, I think I actually started, I guess on page 32 I started talking about this. The more parameters that you estimate in any kind of statistical application, the more variability you will get in your results. Sometimes, estimating those extra parameters will be helpful. But other times, if you're estimating parameters that are not really worthwhile to estimate, what that's going to do is essentially, in a non-statistical way, you could say, add a little bit more noise to your results, and that you will be less certain of your results, and they might not be as good as if you were to, let's say, estimate, a more concise, we'll call it model, that only includes the terms that need to be included.
So is better in this context the lower frequency of misclassifications?
Yep. Yes. So similar to what we looked at with the linear discriminant analysis, we are most concerned about that table.
And in doing that, I could thereby incorporate a differential cost into my decision making. In an HIV test, I might be more concerned about false negatives than false positives.
Yes. So what you could do is include, for example, the cost function. What's sometimes done instead of actually formally including a cost function, is actually look at your classification table. I think that's what you're getting at. Actually look at your classification table and look at your proportion of misclassifications, or actually even the raw number. And that will lead you to maybe choose one method over another. Okay, so let's actually finally get to an application with the place-kicking data set. Now you will notice in this data set, about 89% of the observations are successes. So it might make sense to take that into account then when you do your discriminant analysis. And in fact, what you will see, we get better results when we do take it into account. Okay, so first of all, let's apply linear discriminant analysis. And I'm going to create an object called DA3, which contains my resubstitution results. The reason why, again, that I need to always do resubstitution, or in this case I need to do resubstitution, actually run this set of code, is because I have this validation, this holdout data set, and the only way that I can apply my discriminant analysis on this data set is to tell R, Okay, we're going to use resubstitution here, even though we're not going to look at the direct resubstitution results. And then we can use it then later with the predict function. Okay. Now, this code is exactly the same as when we created the DA1 object. The only difference is I don't specify priors. So I'm going to let priors be proportional. DA4 is going to be the same as DA2, except for I don't say what the priors are. I'll let them be proportional, and I say CV equal true, meaning I do want cross-validation. So here's the output. One thing that you'll notice, so this is from cross-validation here on page 33. Here are my posterior probabilities for observation number 1. Previously, when we had the priors equal, we had 0.11 for population 1 and 0.89 for population number 2 as the posterior probabilities. So you can see that they have changed. You can look at the other posterior probabilities on your own if you're interested. So, now that I have these results, let's summarize the cross-validation results using my summarize.class function. Please note that there is a small error. The 60 and 103 are correct. Just for some reason, my label there, this is on the bottom of page 32, my label was, for some reason I had a 1 there instead of a 0. I must have just accidentally typed it. So, for example, 60 observations that were truly failures were classified as failures. 1,185 observations that were truly successes were classified as successes. Here then the proportions. So 93.9% of the time, I got the successes classified correctly. Previously, we had gotten 78% correct. There. Also previously, we had gotten 76% correct for the failure. So you can see our failure success rate has dramatically dropped, meaning then the corresponding error has increased in terms of for the true failures. So, in an actual application, you might think about that. Do I want to give up my accuracy with these failed place kicks or not? My overall correct classification rate is 0.87. Before, we had 0.78 in the past. So you can see overall I'm doing better. Even though that my failures, I'm misclassifying the failures more often, but since I have so many successes in my data set, this extra part, this extra increase in ability to find the successes is driving up my overall classification correctness rate. Now let's go to the validation data set. So I use my results from now DA3. I put in my validation data there for my new data argument. Here are my posterior probabilities. And let's just jump right down to the classifications. Focus on this table here. You can see that I am getting somewhat similar results to what I did with cross-validation. My overall correct rate is 0.85, which, let's see, do I have that? Which before was 76%. So, looks like overall I have an improvement. And if I were to just simply go on this overall correct rate, I would choose linear discriminant analysis with priors proportional over what I had done previously, linear discriminant analysis with equal prior probabilities. Let's do quadratic discriminant analysis now. the syntax is exactly the same for the function QDA. So I'm going to create two objects, a DA5 that applies quadratic discriminant analysis using priors proportional. DA6 is going to be quadratic discriminant analysis with priors proportional again, but then I'm going to do cross-validation. So this is what the output looks like from doing resubstitution. Not really anything too interesting there. If you remember with linear discriminant analysis, we also had some additional information printed right about here that kind of corresponded to the linear discriminant rule. I said, okay, Ripley rescaled some stuff, so it's not exactly what our rule will look like. Well, notice Ripley doesn't even bother with actually printing that information out. So that's one reason, too, why I didn't show you what the quadratic discriminant rule, the actual form, actually looked like. So here's DA6 doing something very similar. Excuse me. So let's take a look at the first observation. Notice we do have posterior probabilities that are different from what we've had previously. Again, the most important thing is these tables. Okay, so this is on page 36 now. Or 35. So you can see that 91% of the time I get the failure, I get the successes classified correctly. 45% of the time I get the failures classified correctly. So, again, if you are very concerned about these failures, you might prefer this to what we had just been doing with linear discriminant analysis with priors proportional. Because this 0.45 is higher than what we had before, which was about 0.37. Overall correct rate, 0.86 about, which is just a little bit lower than linear discriminant analysis gave us. With my validation data set, again, I get similar results. I just want to emphasize here, notice how the validation data sets in both cases, with linear and quadratic, they had correct classification rates that were lower a little bit than what we got from cross-validation. And relate this back to our discussion where we were looking at how do we measure how good a procedure is. We said cross-validation is better than resubstitution, but still it's typically a little bit biased. So that's why you're seeing this here. You should always expect it to be a little bit higher, generally speaking. So, as you can see here, we've applied a number of different discriminant analysis methods here, and this is what you typically would do in actual application. And then in the end, what you should always do is form a table such as I did here that summarizes everything that you've done and helps let you choose which one method would you go with overall. In this particular case, if I'm not really concerned about, let's say, the failures having a lower classification correctness rate. So if I'm only interested in overall, I like these better, so I would choose linear, the linear discriminant analysis with priors proportional. Yes?
You're only interested in overall, you think if everything is about 88%, whatever.
Well, thank you for foreshadowing what I'm going to be talking about next. I assume you hadn't read ahead and that you were just, because I was doing such a great job teaching, that thought just came to your mind, and, hey, let's think about this a little bit further. And this is what I'm going to say next. Thank you for bringing it up. So, remember, we had about 89% of our data were successes. What if we just say every place is going to be a success? What will be your correct classification rate? 89%, which is higher than what we are getting with these fancy statistical methods. So, the reason why I use this particular example is because it's very helpful for you to maybe step back and see the big picture of what you're doing. You should always do this with every problem. In that perhaps discriminant analysis really isn't worthwhile for this data set. Because if I just say simply every place it's going to be a success, I get a higher classification rate. So if only alone, you're only interested in determining which is a success, which is a failure, not interested in interpreting the effect that these variables have on the response. If you're only interested in classification, then discriminant analysis here is probably not that worthwhile. Any questions about that?
It would seem to me the value in this is not about point after picks. That really, in terms of decision making for the coaching staff up in the booth, it's the 3-pointers they're concerned about. And this data set would look pretty different if you excluded point afters.
Yeah. At this time in the NFL, there were not 2-point conversions. Nowadays, it's always been the case in college football, but nowadays also NFL. The coach actually has a choice. Should he go for 1 point or 2 points? And unless you're Oregon, in terms of in college football, unless you're Oregon, you're always going to go for 1 point unless you need that 2 points at the end of the game, essentially. So in the end, perhaps it would have been better to approach this with only the field goals in the data set. I hadn't really thought of that aspect before until you brought that up. So yeah, you do definitely have a point there. But one reason why I've always kept the PATs in there is actually, and this will be talked about in my Stat 875 course, the probability of success on a PAT is different than a field goal, even if they're exactly the same yards. There is a difference in the probability of success. It is statistically significant. I'll let a coach judge if it's practically significant, but indeed there is a difference. And so that's why I've always kept the PATs in there, even though they are such a large portion of the data set. But you do have a good point. And maybe I'll give a project in the future where I say, for instance, why don't you take all the PATs out and just look at the field goals? I'll write that down.
Well,
Maybe I'll put it on a test here. Yeah.
It kind of pertains to the actual project that you gave us. I'm a subject matter researcher, so I know something about software in hybrid.
Sure.
And there are reasons why you might look at them.
Yeah, I agree. And that was something. And at that time, that was something that came up. Should we include them together or not? And we decided, well, obviously there's going to be differences, but we're hoping that the statistical method then picks the differences out. And that's what we did. I've always thought it might be interesting to go, and this was with the grain science researcher that we were talking about, that we were talking to, who was actually interested in the problem. But I've always thought it might be interesting just to see, indeed, do we get similar results? Do we get better results if we did separate them out? Maybe extra credit for the project. But I mean, if you actually, as you will see, when you do, like, for example, a principal component analysis, you're going to see 2 clouds of points. One's going to be hard red winter wheat and one's soft red winter wheat if you look at the scores in 2 dimensions.
That's probably largely driven by the hardness measurement. Yes. It probably is weighted pretty darn heavily.
Sure. Yes.
Like in this data set, most of the instances are success, right? So isn't there like a way of evaluating like how good you can predict the failures then? Like you said, if we say everything's a success, we get 89% accuracy.
Mm-hmm.
Then isn't it like more interesting to see how good we can predict failures?
I think what you're getting at is, here's where, discriminant analysis would still be important. I think what you're doing, to do discriminant analysis here, and that is, don't focus on this. Don't focus on the overall correct classification rate. Focus more on those.
Mm-hmm.
And in particular, what you're talking about is this one right there.
Yeah.
This is where discriminant analysis still would be of interest. If you could somehow come up with a way to increase that number to a level maybe that you are satisfied with, there's ways to do that by including costs, for example, then yes, what you're saying is that you could still do this. Did I answer your question?
Yeah, somehow like so that in that confusion matrix.
Let's talk about a term. I think it's important to mention this term. You call this a confusion matrix, right?
Yeah.
Okay. I have not used that term yet. This is a non-statistical term that people often use for these tables here. They are classification tables. I call them classification tables. Non-statisticians often call them confusion tables. I want to bring that up because many of you will be reading literature or talking to an advisor, reading literature that's not stat-based, and you will often see that term used. So I'm sorry.
And so, if you're trying to predict failures, then you can look at this in a different way. See which one, like linear or quadratic, are like better at doing this. And well,
yeah, I mean, you could just simply focus on that number. You could do that. Now, this also then leads into something that we will do with logistic regression. And with logistic regression, we're going to come up with what's called a receiver operating characteristic curve. And what that curve will allow you to do is for various ways to apply logistic regression. Look at where your error rates are. It's more flexible than what we're doing right now. It's going to be a nice, it's going to provide some flexibility where you're going to be able to say, suppose I do want 80% correct classification for the failures. I'm going to be able to figure out what the logistic regression method is just like that. Suppose I want 60%. I'm going to be able to find the logistic regression method that will give me that number through using these things called receiver operating characteristic curves. And so, I think what you're kind of getting at is you want more flexibility. You want to be able to control maybe one of these classification rates more than another. And these other methods will allow us to do it. Anyway, also, just to get back to the confusion matrix, and I'm not necessarily talking bad about anybody else's discipline. I've never heard of that term until I came here to Nebraska, and some people were talking about confusion matrices with me. I was like, or confusion matrix. I was like, what? Confusion matrix? What do you mean? That's such a funny name. It's a classification table. Anyway. Okay. So let's take a look at some PCA score plots to help make sense now of our results. So previously we looked at the PCA score plots where I actually put the true result, success or failure, as the corresponding colors of the plotting points. Now I'm going to put in the actual predicted classifications, and this is from the method that I chose, linear discriminant analysis. And so look what's happening here. All the failures are on the left-hand side of the plot. Why is that occurring? Well, this is where you go back to your PCA scores, I'm sorry, your principal components, the actual equations, and then you can figure out more so what this method is doing. And when you look at the first principal component score, you'll notice that distance plays a very, very important role in finding PC number 1. Large distances are negative PCs, PC number 1s. Short distances are the positive or the larger PC number 1s. And again, for football fans, and I think most people here, it's intuitive that the longer your distance is, the harder it is to make the place kick. Okay, and that's one reason why I like this data set, because there's a lot of intuitive aspects to it, and you can see what the discriminant analysis method is doing there, and that is it's saying those longer place kicks which will be on the left side, they're going to be classified as failures. Now, also what you're seeing here too, you see some stuff like this, kind of a dividing line there almost between failures and successes. And so you might be thinking, well, what does principal component number 2, what's that doing that's causing us to see that? Well, if you look at principal component number 2, it's actually highly dependent upon the type of the place kick, meaning is it outdoor or inside, and also the field variable, which means grass or artificial turf. And typically, you think of grass as being maybe more difficult to kick off of than artificial turf. Also, you typically think of outside being more difficult than inside of a dome stadium. And if you look at the zeros and ones in terms of what those variables represent, corresponding to what the principal component score gives you, it will make sense for why you're seeing this kind of a line there that's occurring on that kind of a plot. And essentially, as you add more risk factors to your place kick, the likelihood that it's going to be classified as a failure increases. You can also look at some 3D plots too. I'll let you look at those on your own. Let's see. You can look at what's on page 39 on your own too. Or top of page 39. So now this gets out of the example. Suppose a variable of interest is qualitative with three levels, A, B, and C. How would you include this variable in this discriminant analysis? So it's not numerical. You have think of this as almost like an independent variable. You want to include this in your discriminant analysis. You want to include these levels A, B, and C. We've seen these qualitative variables, like for field. It's a 1 for grass, 0 for artificial turf, right? I could have just simply put the characters grass, or the words grass, and also artificial as the variable values.
Where are they nominal? Do they have an order? A, B, C?
Let's say that they're not nominal. I'm sorry, that they are nominal. They are not ordinal. So they don't have necessarily ordering to them. These are just dummy variables, or dummy symbols to represent the three levels. So maybe in another application you might think of political party affiliation, Democrat, Republican, Independent. Well, that is ordinal, yes. I guess it could. Depending upon how you look at it, it could be ordinal, but let's say it's not. Okay.
Okay.
So change it to 0, 1. But how do we change it? Do we just have one variable that's a 0 or 1? 2. So, especially many of you have taken like a Stat 870, 875 class, in this case, you need to create what are called indicator variables. So in particular, in this case, what you can do is this. Let's see. So you have three levels, A, B, and C. Now I'm going to do it how R does it, okay? And what you're going to do is create two new variables that you would actually use to do your math. When you're finding the covariance matrix, when you're finding the mean vector, all that stuff. And this is how you're going to create the two variables. This is how R would do it. Where level A is going to have a value of 0 for variable 1, a value of 0 for variable 2. Level B is going to have a value of 1 for variable 1, 0 for variable 2. And lastly, C has a value of 0 for variable 1 and 1 for variable 2. This is how you code a qualitative variable in a numerical manner that you can include in discriminant analysis. You can actually include in any kind of regression model. And the reason why this works is because notice that each unique level of this qualitative variable, A, B, and C, has a unique coding amongst the variables. That's why this works. Now you might be thinking, well, why don't you just have a variable 3 here and code it like that? Why not?
Well, you have some code that you don't have a variable for. Like if you get 0, 0, 0, what would that be?
I guess that would be one perspective. I'm thinking more of a mathematical perspective. Actually, as strong a collinearity as you could have, I'm looking for something else. Well, thank you for offering a suggestion. What I'm looking for is that simply in this situation, you won't be able to use these variables because you're going to have linear dependence amongst your variables. We talked about this in the matrix algebra section, and you can try this on your own. I think that's maybe the easiest way to look at it if you're not maybe with a strong math background. Just simply create a data set that has a qualitative variable, and so you code, let's say, a qualitative variable of 3 levels, and you code 3 indicator variables. Indicator meaning, indicator is a word meaning it's this or it's not. And just create a data set, maybe in regression. Then just make up a response variable too. Try to fit the model. You're not going to be able to. Because at some point you're going to need to find that x prime x inverse matrix. You're not going to be able to find an inverse of will not exist. Okay, that's the reason. But the main thing is, notice with only 2, you can uniquely code a 3-variable qualitative variable. So that's how you would take that into account. Okay. Fortunately, we did not get as far as I wanted to. We will just have to pick up on continue with discriminant analysis next time. And I guess that's it for today.